Okay, so this is going to be the first of a couple of sections on how do we do um, double integrals over more general regions. All right, so we're going to start off with a little bit of theory here, and then we'll work down to something that is more um, easy to see. Okay, so like the 3D dimensional or three-dimensional image of this is that I have some general region D in the floor, and above this I have some surface, and kind of around here I have some sort of solid between that domain in the floor and the surface, right? So if I am looking down at the floor, right, in my XY little world here, I have this strange region that we are calling D. And what I'm going to do in order to find this thing is I'm actually going to stretch a rectangle around it, which we're going to call R. Okay, and ultimately we're going to build like a function here. So if xy is in D, then we're going to say the function big F of xy is going to be equal to little f of xy. But if xy is in R but not in D, so it's like R minus D, big F of xy is going to be 0. Okay? Because I only want to add volume if I'm over D. If I'm in R, not over D, I'm going to add 0. So this is going to give me kind of a function that I can work with that'll allow me to take an integral. So usually these regions set up in one of two ways, and we're going to look at the type 1 way today, and in a later video we're going to look at the type 2 way. So in the type 1 way, I have my x coordinates are going to be bound between A and B. Now, D is going to be a region running from A to B, bound between two functions. One, which is y equals g sub 2 of x, and the other one is going to be y equals g sub 1 of x. Okay, so this is D. So what I'm going to do is I'm going to imagine that there's R is some rectangle here, right, which is surrounding D. Okay, so if I do that, the double integral of D of f of x y dA is the double integral of R of big F of x y dA. Okay, so that means when I'm over D, we're counting it as f of xy. When I'm in R somewhere else, I'm counting this as 0. So this is an iterative integral from A to B from, well, let's call this here C to D, from C to D of big F x y dA. Now, note, wherever y is less than g1 of x, or y is greater than g1 of g2 of x, wherever that is, f big F of xy is going to equal 0 because it's in R but not in D. So I can rewrite this using those as my upper and lower bounds. Sorry, this should be dy dx. I missed the y bound there. This should be the upper and lower bounds for y. Okay, so carrying over, we have a to b, c to d, big F, x, y, dy, dx, right? But we've got this idea that if I'm above G2 or below G1, then big Fxy is 0. So this is going to be the same as going from A to B, but now I want the region between G1x and G2x, right? So these bounds are now going to be functions of x of big Fxy dy dx. But when I'm not between these two bounds, this thing goes to 0, but I'm in between them. And since I've restricted myself to being in between them, I now can go back to this being little f of xy dy dx. So kind of had to use the big Fxy to gain an understanding of the problem. And then I can, once I have the understanding of the problem, we can return back to the little Fxy. Okay, so let's actually work an example of something like this and get a solution. All right, so let's define a good type 1 region. So we're going to make D equal to the set of all x, y, such that x is going to run from 0 to 2, and y is going to be trapped between x squared and 2x, right? So this is the parabola kind of going upward, right? 2x is a line going like this, so D is kind of like that region in there. All right, so volume then should be the double integral over D, and we're going to make our function f of xy be x squared plus y squared dA. All right, so this now becomes the integral from 0 to 2. The integral from x squared is on the bottom, right, to 2x on top of x squared plus y squared dy dx. Right, so I'm integral from 0 to 2. This one becomes x squared y. This is going to become a third y cubed from x squared to 2x dx. So the integral from 0 to 2. Let's see, if I put 2x in here, I'm going to get 2x cubed. That's 2, not 3. So write that so we can read it later on. 2x cubed. If I put 2x into here, let's see, I got a third. 2 cubed is 8, so that's going to be 8 thirds x cubed minus, let's see, that's going to be x to the 4th plus 1/3 x to the 6th dx, right, 2 cubed, there we go. All right, so let's see what happens here. We got 0 to 2. Let's see, 8 thirds and 6 thirds is going to make me 14 thirds x cubed minus, let's see, that's x to the 4th minus 1/3 x to the 6th dx. All right, so this is just an ordinary integral at this point. So let's go and get some room and work with that one. All right, so we have an ordinary integral from 0 to 2 of 14 over 3x cubed minus x to the 4th plus, no, minus 1/3 x to the 6th dx, right? So this is going to go 14 over 12 x to the 4th minus 1/5 x to the 5th minus 1 over 21 x to the 7th from 0 to 2. Okay, so the 0 doesn't matter because this is all going to go to 0, so let's put in the 2, right? So this is 7 over 6 times, let's see, 2 to the 4th is 16, minus 1/5 times 32, minus 1 over 21, so 6th would be 64, 7th would be 128. All right, so I think this is 112 over 6 minus 32 over 5 minus 128 over 21. And you can either find the common denominator or slam this into a calculator, which I think I just slammed it into a calculator. It gives me 216 over 35. All right, so there's an example of working a type 1 type problem. In the next video, we'll look at type 2, and then we'll give some more examples, and we'll go from there. All right, so there we go. It's double integrals over general regions, part 1.